Okay, now we start lecture 5. It's about the port addressing mode. It is an addressing mode used to point to ports connected to your system, to the microprocessor system. You have two instructions that go with the ports. Ports are interfaces with the microprocessor that enables it. These interfaces enable the processor to bring data in by the in instruction or send data out by the out instruction. So they are connections to the system which enable the system to send data to the outside world and bring data from the outside world. Okay, the addressing mode of ports are of two types. A direct addressing mode, where you give the address of the port directly, or you place the address somewhere in a register, which we call it indirect addressing mode. So indirect, the address is given inside a register. Direct, you immediately give the address. Okay. The direct addressing mode, the port number is given directly within the instruction. For example, NAL, 15. 15 hexadecimal is the port number. So what this instruction says is this: go get 8 bits from a port whose number is 15, place them into AL. Okay, good. The indirect addressing mode, you place the port number inside the 16-bit register DX. So if you have large ports, many ports, large number of ports connected to your system, this may require more bits to address and give number to these ports. This is why then DX will be used. Okay, for example here, all right, we don't have any square brackets because even the number inside DX represents an address. You don't include DX within square brackets because it is only used with the N instruction. So what this instruction says is this: take the number inside DX, that number refers to some port, go to this port, get 8 bits out of this port, place them inside your AL. So this is the indirect addressing mode of ports. Alright, now the program memory addressing. This is the second type of addressing mode. The first type deals with data, while the second type deals with program memory. Okay, program memory, we address some instruction by the jump to jump to some instruction given a label or an address, and as well the call instruction. It refers to some instruction inside your code memory segment. It's given by this call. Okay, you call some subroutine or some program placed somewhere else aside from your main program. You address this by the call, and here you jump to some instruction by the jump. So jump addresses some memory location inside your code memory segment, as well as call. Call as well addresses a memory location inside your call memory segment. They can be divided into direct, okay, relative, and indirect. And when we go to jump and call, we will know the difference among these three modes: direct, relative, and indirect. Okay, now let's talk about the stack memory segment. There is a dedicated memory segment called the stack memory segment among the four active memory segments. We have the stack, the data, the code, and the extra. This stack is actually used to hold data temporarily. When you call some subroutine within the main program, you go to some subroutine and execute the instructions inside these subroutines. Then you're finished with the subroutine. You would have to go back to the next instruction, to where you left. To know the address of this location, you place it inside your stack. So you know after finishing executing the subroutine, you know where to go to your main program. Okay, we call these return addresses. Okay, so you store your return addresses inside your stack. The stack is of a LIFO type kind of memory, so the last bytes that is stored in your stack is the first to go out. Because if you have, let's say, 3 nested loops, and you go from the first loop to the second to the outer loop, when you come back from the outermost, from the subroutine, you go first to the outermost, then the middle, then the innermost. So it has to be last in, first out. So the last information stored in the stack is of the outer loop. You have to go first to the outer loop, then to the middle, then to the inner loop. This is why it is of LIFO type of memory. Last in, first out. Okay. You store data into the stack by push or call. So when you push some register into the stack, you store data into the stack. When you call a subroutine, you store return addresses into the stack. The data stored in the stack by pushed are coming out by pop, and the data stored in the stack by call are reached by the return. Okay, and we have two registers to be used with the stack. The stack segment register, in which we store the beginning of the stack, the address of the first byte inside your stack, and SP, which points to the top of the stack. See, if you have a stack memory segment, two registers goes with the stack. SS, in which the address of the first byte is stored, and SCP, in which the address of the top of the stack is stored. Okay. How do we store a word to the stack? We have 16 bits. We need to store them into the stack. Okay, the top of the stack is now pointed to by SCP. So the higher order byte is stored in SP-1. So you go one place down and store the higher order byte. You go two places down, SP-2, to store the low order byte. Then SCP is decremented by 2. Okay. Example, push AX. We have 16 bits. We need to store them into the stack by instructing the assembly instruction push. Okay, this is the value of your AX. This is the value of the address of the beginning byte in your stack, and this is the top of your stack. You need to go one location down to store the 12, and one more location down to store the 34. Okay, here is your stack. This is SCP, the top of the stack, and this is, you go one location down to store the 12, and one more location down to store the 34. Okay, here you are, 12 and 34. Then your SCP goes two locations down. It will point to this. Okay, your SP now is FFC. So these are logical addresses. You have to add this times 10 to these logical addresses to get the physical addresses. Okay, how do we remove a word from the stack? The lower order byte to which now SCP points is retrieved first, is removed first. Then the higher order byte you have to move SCP-1 place up to get the higher order byte. Then your SCP is moved twice to memory locations. Okay, how to pop AX from the stack? Okay, here is your stack, your SCP is at this location. Now 34 is popped out first, and the stack goes up one location. Then the 12 pops out second, and your stack go one more location up. So after finishing popping up AX, your stack pointer should point to this location, and this data should be obtained, should be got out of your stack. Here again are your physical addresses, while these are your logical addresses. So the stack pointer now will point to this location. Okay, F F F E, the top of the stack. Okay, let's now talk about the program control instructions. Instructions with which you control your program. Okay, usually you control your program with jump and some subroutines. And to control the program with these instructions, jump and call, you call a subroutine or you jump to somewhere inside your code. Alright, you use your flag control instructions to help you do this. So these instructions affect the flags inside your flag register. These are: you clear the carry flag bit, you set the carry flag bit, you complement your carry flag bit, you clear your interrupt bit, you set your interrupt bit, you clear your direction bit, you set your direction bit. So these instructions help you control the flow of your code. Okay, let's talk about the jump instructions. You use jump whenever you need to skip a portion of your code and start somewhere else instead of going to the next instruction and execute it. So you need to jump to somewhere else inside your program. Okay, so sort of altering your execution path. And instead of going sequentially to the next instruction, you skip few instructions and you go to a specific instruction you are interested in. Okay, when you do this, you don't intend to return back to where you left. You do this with the call, when you call a subroutine. But with the jump, you skip a few instructions and you proceed executing your program sequentially without going back to where you left before the jump. Okay, jump instructions are used to change the CS and IP. So CS and IP controls where you go. If you need to go to somewhere inside your code memory segment, you change your IP only. If you need to go to outside your currently active code memory segment, you would have to change both your CS and IP. Okay, we have two different types of jump instructions. Unconditional jump, so you jump for the sake of jump. No condition to meet to do this jump. You don't check any condition. You don't go and check any of your flag bits. You just jump because you don't need to execute a few instructions inside your program. This is called unconditional jump. And there is also a conditional jump. You do the jump after satisfying some condition. If a condition is met, you jump. And the condition is usually checked through your flag bits. Okay, the unconditional jump, you don't have any condition to be imposed or to be checked. You jump for the sake of jump. While in a conditional jump, there should be some condition you check before you jump. So your jump instruction is not going to be executed unless the condition is met. Otherwise, you don't jump. If the condition is not met, you don't jump. You go to the sequential instruction, the instruction that its turn comes. Okay, and this is the end of lecture 5. So the conditions are checked through these flag bits, and the unconditional jump is given as this is jump, this is the mnemonic code of the jump, which is unconditional. You jump and you give the operand to tell your processor where to jump to. It needs an operand, and the allowed operands are short, near, far, or a 16 memory pointer, 16 register pointer, or 32 memory pointer. And this we'll discuss in the next lecture, lecture 6. Okay, see you at lecture